Well, Frank, it's nice to be here with you today. I'm glad I had this opportunity. You said in your Nobel acceptance speech that you personally are a product of both harmony and conflict between China and the West. Can you tell me what you meant by that, looking especially back to your early years, how the history of that time led up to your introduction to science and math?
You know that China had a very long and distinguished history, but by the 19th century, China was in a very sad state. There was no modern science at all. And great powers, mostly Great Britain, had tried to carve up China. And then there was a war in 1900 called the Boxer War, and during which 8 armies, including some armies from the United States, occupied Beijing and signed a treaty. The treaty stipulated that China was to pay 450 million taels, that means ounces of silver, an astronomical amount at that time. In about 10 years or so after that, the U.S. Congress passed a law which said that part of that, the American share of that 450 million taels of silver is to be returned to China for educational purposes. And a foundation was set up, and the money from the foundation was used for 2 purposes. One, to establish a university in China, which is called Tsinghua University, one of the most famous universities now. It's one of the earliest modern university in China. I was a direct beneficiary of that because my father was a professor of that university since 1929, and I grew up on that campus. Another part of the money was used to establish scholarships for Chinese students to come to America to study, and I won one of those scholarships. So in 1945, I came and became a graduate student in Chicago. So in 1957, when I stood in front of the King of Sweden and the assembled people, I was moved to reflect on my own history in the context of the history of China and the relationship between China and the West. So that's why I said that I was a product of both cultures in conflict and in harmony.
In your early years, you said you wrote in your Selected Papers book, as I recall, you had a tranquil childhood, which was already a privilege, I suppose, in that time. Eventually, however, the war arrived and touched your life and brought you to the Southwest
Associated University, yes.
Can you comment about that? What opportunities were there for you in these very difficult times?
I was very, very fortunate. When I was an elementary school student and a high school student, most of the children my age did not have enough to eat, did not have enough clothing. China was in an extremely sad state. It's when you look at some of the movies about the people in Africa today, I think that's the order of magnitude of the state that the Chinese children mostly were in at that time. But because my father was a professor, Tsinghua University had a gate. It's a had a fence, and so inside of the fence we live a completely different life from most of the kids my age at that time. So I was able to get a very good elementary school education and high school education. But all during those years, Japan was making inroads into China. First, Japan got the Manchukuo, which is northeastern China. Then in 1937, they tried to occupy Beijing. So the whole university moved to the southwest, and that's where I went to college from 38 to 42. The trek from Beijing to Kunming was a long and arduous one. And millions of people moved south. So it was a very, very sad state. But at the university, however, perhaps because everybody, both the staff and the students, felt that during such difficult times, it was possible to do some scholarly research and learning. One must treasure every moment of it. That may be one of the reasons that many of my classmates, my university mates, later became very important scholars, both in China and in America. So I, in some sense, was very, very fortunate under these very difficult circumstances. Somehow, I was able to have a academically oriented background throughout my elementary school, high school, and university days.
You wrote in the selected papers about, well, we were somewhat out of date. The journals would arrive a few years late when you were in the Southwest Associated, but they arrived.
Yes.
Do you have a sense of that there was a sense of being connected to the outside scholarly world despite everything?
Yes. I had earlier referred to my father. My father was sort of the first generation of Chinese scholars who got PhDs abroad, who introduced, after they returned to China, modern science to the next generation. So by the time that I went to the Southwest Associated University, China was in some sense, at least in that small corner, well connected with the outside world. So the courses I took in that university were completely up to date. In fact, I took a course of quantum mechanics. After 46, I took the same course at Chicago. Chicago at that time was one of the most, the greatest physics departments. And I found that the course I took in quantum mechanics in China was education-wise much better than the one taught in Chicago, partly because the one taught at Chicago was taught by Edward Teller. Now, Edward Teller was a brilliant physicist, but he was too busy. He didn't have enough time to prepare the lectures, so he got stuck in class periodically. But reflecting on that, I found that experience of Taylor getting stuck very educational. It's because of the following. Since I already knew quantum mechanics, so when he got stuck, I could observe how he was trying to get out of that, that bad situation. And then that taught me something. I realized to Taylor what is important, what is not important. So that was also very educational for me.
Well, the the commitment to higher education in very difficult times, to say difficult economic times, is of course understating it tremendously, is maybe a lesson that we can learn here in the United States in these much less difficult times, relatively speaking. Now, you referred to the course you took in quantum mechanics at Chicago, but you came to Chicago through New York. As I recall, you took a boat through India up into New York, and when you arrived in New York, as I understand it, you were searching for Fermi.
Yes.
Could you tell us the story of how you came to Chicago from whichever pier you landed on?
When I was in Kunming during my university days there, I really had a very good foundation about modern physics. In particular, I already developed a certain taste. And the modern physicists that I most admired were Einstein, Dirac, and Fermi. All three of them were great physicists of the 20th century. Now, Einstein didn't have that many graduate students. Besides, he was very old by the time that I arrived in America. So he was out as a possible thesis advisor. Dirac also didn't take many graduate students, and he was in England anyway. And Fermi was the one that I very much admired, and I wanted to be his graduate student. So when I arrived in New York, I arrived in New York and not in San Francisco, because that was the end of the war. There were no commercial traffic between China and the U.S. The only way to come to U.S. For me was to get a berth on one of the troop transports, which were sent. They are called Liberty ships. They were about 5,000 tons each, and they would transport something like 3,000 American soldiers from the China, Burma, India theater back to the United States. So I got one of those berths in Calcutta, and the ship took us through the Red through. There was a person in New York. I won a scholarship, and there was a person who manages that scholarship in New York, and he rented rooms in Edson Hotel, which still exists in Times Square. I took Fan there one day recently and sat in the lobby. It's full of Art Deco styles. After one day, I went to Columbia. I took the subway to Columbia and went to the Pupin lab, trying to look for Fermi. But the secretaries of the department didn't know who Fermi was. I was really surprised because it turns out that Fermi had been absent doing classified work. Those secretaries were new, so they didn't know about him. So I was very disappointed. So the next day I went to Princeton, and I did see Wigner, but he said he was going to be on leave for half a year at the Oak Ridge. So he couldn't be my thesis advisor. Then he said, how about you're working with Wheeler, with John Wheeler? So I went to see Wheeler. I don't know whether you have met Wheeler. Wheeler was, he just died, I think 2 years ago, at the age of approximately 100. Wheeler, you know, is a very serious person. He really make any jokes. And when I saw him, he gave me a list of some 10 items which he gives to graduate students, which were topics that he thought would be useful to do research on. I remember some of those still. One of them was to find which of the experiments which said the mass of the meson was 50, the electron mass, 200 the electron mass. There was a spectrum of them. Mm-hmm. And one problem was to study and decide which one is the most reliable one. Another was about the geophysical effect on the cosmic ray. Those were all very interesting problems, and many years later, I could not help but wondering if I had stayed as a graduate student of Wheeler, what would happen afterwards. But anyway, while I was still debating whether I should remain in Princeton as Wheeler student, I heard that Fermi had decided to go to Chicago. So I quickly cabled the University of Chicago for admissions. And my grades were very good in China. So they cabled back within 1 week, saying that they accepted me. That's how I became a student in Chicago.
So, but there it was Teller who was actually your advisor, at least in some formal sense. Is that right? Although you worked in a lab for a while.
The reason is because on the way to China, to America, I said to myself that I had learned a lot of theory, but I had no experience doing experiments. So I decided I should write an experimental thesis. So when I got to Chicago, when I saw Fermi, in fact, I arrived in Chicago a few days before New Year's Day, 1946. That was also approximately the time that Fermi arrived from Los Alamos. And so I went to see him. I said I wanted to do experiments with him. I had very strong recommendation letters. So he was willing to entertain that. But after some investigation, he said it couldn't be done because he was doing experiments in argon, and argon was classified completely at that time. So he suggested that he made two suggestions. One, I would work with Edward Teller on theory, because he said Teller has many, many ideas, many, many graduate students. And another suggestion was that if I want to do experiments, I could work with Sam Allison, who is an nuclear experimental physicist, who was in fact Oppenheimer's deputy at Los Alamos. And so I first went to study with Teller. Teller was a brilliant physicist. And also, in person, he was a very warm person. So he sort of immediately embraced me and gave me several problems. I worked on them, but Taylor's approach to physics and my approach to physics are not quite the same. He is more willing to make approximations. I'm less willing to make approximations. Different styles of approach to physics. So I learned a lot from him, but none of the problems he assigned to me produced a paper. So I went to work with Allison. I worked in Allison's laboratory for about 20 months. And that was very educational for me, because I learned that I'm not born to be an experimental physicist. I was clumsy in the laboratory, and all my fellow graduate students laughed at me for my doing all kinds of wrong things. But they liked me as a person, especially because I can solve theoretical problems for them. So we were on very good terms. And then come 1948, this was 20 months after I became Allison's student, my experiment was doing very poorly. I was very famous in Chicago at that time. You can imagine, because there were not that many Chinese students in America at that time, not like now. And here comes a very thin Chinese student who seems to be doing extremely well. In fact, not to be bashful, I beat all of my fellow graduate students hands down. So they all knew that this Chinese graduate student is having great troubles doing experiments. So one day, Taylor came to the lab and said, Frank, I understand you are not doing well in your experiment. I said, yes. He said, you had written a short paper. I found it to be very good in theory. Why don't you just fill it out so that it becomes longer? And I would accept that as your PhD thesis. That produced a strong emotion on my part. So I thanked him and said, thank you. I have to think about this. So I thought about it for 2 days and decided he was right. I finally understood I should not try to be an experimental physicist. So I went back to him, and he said, fine, but it's a bit too short for a thesis. Can you make it longer? So I went back and added 2 pages to it. Many years later, Taylor, at one of my birthday celebrations, said, this went several versions, several times, and eventually it reached the 11 pages, and he decided there's no more use arguing with me, so he accepted that. So that became a very short thesis, but the thesis was very good, and in retrospect, the thesis was using symmetry and group theory about nuclear reactions. That turns out to be the main general theme of much of my subsequent work. For some reason, as a graduate student, I like the concept of symmetry. I like the mathematical formulation of the concept of symmetry as applied to natural phenomena. That became one of the main themes, or perhaps the main theme of my subsequent work.
I believe while still at Chicago, you did eventually write a paper with Fermi.
Yes.
About the possible composite nature of the mesons.
Yes.
And at the beginning of that paper, you and he remark that as the number of so-called elementary particles increases, the chances that they are truly elementary decrease. Yeah. Words to that effect. How did that paper come about? And in some sense, it anticipates a great deal of work in the subsequent years.
The main idea was Fermi's. And at that time, people sort of accepted many of these new particles as elementary particles. Fermi said to me, this may not be true. Why don't we study whether the meson could be composite? So we began to collaborate on that. I remember that was in the summer of 1949, and Fermi's family was, I think, in Italy or someplace. So Fermi was a bachelor, so we spent a lot of time together. And so I learned, I've taken Fermi's courses and had attended his special courses, evening courses, and learned the style of Fermi about how to approach physics. But this collaboration became a very close contact. After we did some calculations, I thought that the question was interesting, but I didn't feel that what we said could be verified experimentally. So I was not proposing that we would publish it. But Fermi said, no, we should publish it. He said, I remember distinctly. He said, as a student, you learn problems set by other people. As a researcher, you should set the questions yourselves. So we may not have hit the right composition, but just raising the question is important. So we published a paper.
Well, another paper that you commented on thinking about whether it would be published or not, although in this case the answer was simple, was the paper with Mills on gauge theories. Now, looking back from here, the time from your arrival to the time of that paper, which was 1954, if I remember right, is not so long from this perspective. Can you give some trace of how it developed, how it came to fruition?
I think I was very, very fortunate. I had earlier referred to the fact that the paper I wrote for my PhD thesis under Teller was about using symmetry, the concept of symmetry, and group theory in mathematics to apply it to natural phenomena. For some reason, that was something that I already, when I was in China, was very much interested in. I was very fortunate that I got onto this track or this particular aspect of the structure of physical laws that early. So when I was a graduate student in Chicago, beyond that paper that I just referred to about, which became my thesis, I studied the question of symmetry. And in particular, one important mathematical expression of symmetry was called gauge symmetry or gauge invariance, which was invented by a great mathematician named Hermann Weyl in 1918. I was hooked on that idea. So as a graduate student, I scribbled some notes. And these notes I found a few years ago in my papers. And so they have now been republished. If you read those notes, you see that I was trying to say maybe this gauge symmetry idea could be used to generate a theory of how these elementary particles would interact with each other, what forces they exert on each other. So that key idea I already had. But to implement that, I got stuck. So I would work on it for a few days and abandon it. But then after 2 years, there were more elementary particles found. There are more desire to study how they relate to each other, how they interact with each other. So I would come back to this idea and then got stuck again with the implementation. This took place several times until 1954. In 1953, I was already at the Institute for Advanced Studies for several years, and the Brookhaven National Laboratory had a new, the world's largest accelerator at that time called Cosmotron, just beginning to operate. They want to get some young theorists to help the experimentalists there. So they asked me to visit Brookhaven for 1 year, 1953 to 1954, which I did. And they assigned a small office for me, and they assigned the office mate, and that turned out to be Bob Mills. Bob Mills was some 4 or 5 years younger than I, and he was just about to get his PhD, and he got a job as sort of a pre-PhD postdoc at Brookhaven. So we shared the office. And of course, we began to talk about the various aspects of physics. I found him to be very intelligent and with wide-ranging interests. So naturally, we began to discuss this unfinished idea about how to use gauge symmetry to create interactions between particles. And then we got stuck at the same place. When Bob and I, years later, recalled, we were both vague about what precisely happened. But we said, apparently, that the reason that it doesn't work is because a fundamental formula which we copied from Maxwell may need some amendment. So let's add a term to it and see what happens. We added a quadratic term. At the time we said, if the quadratic term still does not work, we'll add a cubic term. But fortunately, when we added the quadratic term, after a couple of days of calculation, not very long, today we can teach to the graduate students in 1 hour. We found that all the difficulties disappear. All this very complicated formula, which became longer and longer, all cancel each other out, so that we got very beautiful, compact equation. So we knew we got something. Then there was a long struggle because the idea was beautiful. The structure was very beautiful. But how do you compare that with experiments? And there was one major problem which we couldn't solve, namely, according to what we structured, it was a set of equations. It apparently gives zero mass particles, lots of them. But there were no such zero mass particles to be found. So that was a big obstacle. In fact, in February 1954, while Mills and I were still doing this, Oppenheimer, back in Princeton, heard about it. And also, Pauli was visiting Princeton, and Pauli was interested in the idea. So Oppenheimer called me up and said, Frank, why don't you come back to Princeton and give a seminar on what you're doing? So I did. And at the seminar, Pauli gave me a hard time because he was interested in it, and he also knew that the idea would produce massless particles, which were not experimentally found. So he kept on raising this question. So I had described that experience in my selected papers. After that, for some 4 months, Mills and I tried to solve this problem. We couldn't. But we felt that the idea was very beautiful. So we wrote a paper. At the end of the paper, there was a paragraph discussing this particular question. Why are there massless particles? Why we apparently were creating a theory with massless particles which were not experimentally found. That section was very difficult to write because we didn't know what the solution was. But today, with hindsight, if you read that section, what it essentially says is that there cannot be massless particles. So there must be something in addition, which we do not know. So we ended the paragraph in that note. I think in retrospect, we were smarter in this case compared with Pauli, because Pauli confronted the same question, and he became discouraged, and he never published anything about it. At that time, the editor was Gouchmit. We sent in our paper for publication. No questions were really asked. He accepted it without any questions, so within 2 or 3 months, it was published. Of course, now it has become a very important paper because later on, there were additional ideas, very important ideas, called the symmetry breaking, which became very successful starting in the 1970s.
Well, in that period between the mid-50s and 1970 already is 15 years, I don't think the paper was certainly not unknown, but it was considered, I remember even as a student hearing, it was considered somewhat mysterious. When did you become aware that these theories were emerging as the theories of what's now called the Standard Model? When did it become clear, and did you have some faith that this eventually might occur?
It was a gradual process. If you ask, when is it generally accepted that this idea is correct, after you add the symmetry breaking idea to it, that really was in 1972. So all between 54 to the 70s, what happened was, for example, our paper was published in 54. Nobody ever invited me to give a talk in the next 10 years about the subject. I did give a talk at Harvard, but what happened was Harvard was looking for a young professor. So they were interviewing various people, so I was one of them. But they didn't assign a topic for me to talk. They just say, we want you to come and give a seminar. You name the title. So we talked about this. I remember that I talked to a large audience, and at the end of that, there was not a single question asked. In the audience, there was Ramsey, there was Schwinger, there were many people from MIT. I think the general view was that the idea is very beautiful, but it has nothing to do with physics.
What year? Do you recall the year?
That talk was in 54.
Oh, it was, right then.
Yes. Now, after that, as I said, nobody ever invited me or Bob to give a talk on the subject. But then about 7 or 8 years later, I think in late 50s, Murray Gell-Mann somehow became interested, and he generalized what we did to a bigger symmetry. But of course, that paper also did not immediately materialize as something agreeing with experiment. The Russians got onto it also around 1960, because I was sent a Russian book, which is a collection of papers about related to the subject, which shows that by the early 1960s, there were scattered people in the Soviet Union who found the idea interesting. So there were several papers, in fact, there were many papers written, but some of them were collected in this little book. The crucial development which made gauge theory important was first because of a paper in 1967 by Steve Weinberg. Steve Weinberg said that if you marry the gauge idea with symmetry breaking in a specific context, the problem with symmetry breaking is that it's not unique. Gauge theory is quite unique. Symmetry breaking is not unique. He said that he proposed one particular version of symmetry breaking and said that this might work. In addition, he predicted, predicted is too strong a word. He sort of said, perhaps the whole theory is renormalizable. Renormalization is an important requirement for any theory of this type. And he did not prove that it's renormalizable. But he sort of guessed that it might be renormalizable. That renormalizability was proven in 1971 or 72 by a young graduate student in Netherlands. And also at the same time, experiments began to show that this combination of gauge theory with symmetry breaking produced some experiments which were found to be correct. So starting about in the early 1970s, two things. One, these experiments. The other is the renormalizability pushed the idea forward. And then it became sort of a idea which dominated the field. And amazingly, since that time, with thousands of complicated and beautiful experiments, more or less the original idea of Weinberg's combination, Weinberg's choice of how to do symmetry breaking seems to agree with all experiments. What's the lesson that one should learn from this? Is that I would say, A, one should explore beautiful ideas. B, one should not be deterred if one beautiful idea does not solve all problems. C, I think editors should not be too harsh on people who write exploratory ideas.
Generally, in that time, both before the early 70s and after this creation of the modern theory that uses of elementary particles that uses gauge non-abelian gauge theories, you left the applications to elementary particles in general to others. You concentrate, as we'll talk about, in the mathematical structure, but it indicates, well, it's a personal choice. Maybe you'll comment on why you didn't get involved so much in what we now sometimes describe as model building.
I think that's a very complicated question because that involves psychology.
Well,
you know that every research worker has certain likes, certain dislikes. When Weinberg was doing the 1967 paper, what was my attitude to it? In retrospect, I should have rushed and explore whether the idea is correct and whether it should be modified or so on and so forth. I didn't do it. And not only that, in some sense I was opposed to it. I was opposed to it partly for some philosophical reasons, which in fact I had detailed in my selected papers. But also, here it reflects on something which I think the general public may not sufficiently appreciate. Because every research worker has a certain style. And if somebody else proposes a style that is not exactly along his lines, there's a natural resistance to it. The resistance, in retrospect, may be totally irrational, but it's psychologically very natural. So part of the reason that I did not further explore that symmetry breaking, part of it was based on some general philosophical ideas. Part of it was the psychological element. Actually, there's a third. Because at that time, I was heavily engaged in many-body problems, statistical mechanics. I was making big headways in it. So therefore, I did not spare time back into this area. But I think that young research workers should be aware of the fact that your emotional reaction to what you like and what you do not like is a fact of life. You should be aware of it. I would not say that you should abandon that, because if you have some resistance to something, that may be in fact the right thing to resist. It's in the frontiers. This is a little bit like fashion, women's fashion. You may have a new idea about fashion, which may or may not blossom. And you have to realize that both you must insist on your own ideas, and yet you have to realize that your direction may not be the right one. This is a complicated process.
It was a metaphor I wasn't anticipating. In the intervening times, with the successes of the Standard Model, people have talked once again about an idea that's so often associated with Einstein, the idea of sometimes called a final theory. Of course, string theory and its variants have been widely investigated in that connection. So what are your thoughts about this idea of finding a fundamental theory upon which we're unlikely ever to advance or to improve?
Perhaps the greatest and the most original idea of Einstein. Einstein did many things, many beautiful things, many important things, but perhaps the most original of his ideas was the creation of general relativity. And after he created general relativity, you might say that Einstein has changed. This has been commented upon. He realized that, in his own words, you can understand nature by pure thought. And along that direction, he then wanted to create a unified field theory. Unified field theory is the final theory that some people refer to, sometimes called theory of everything. Now, with the gauge idea, with the symmetry breaking, of the four fundamental forces of nature, three of them have become well understood through this combination of gauge theory and symmetry breaking. But the one last one, gravity, which was what Einstein had worked on originally, remain not tractable. It's not tractable because if you marry general relativity or gravity with quantum mechanics, you get into a mess. It's not well understood. And that is what prompted people to launch the idea of string theory. Now, string theory has been in existence for at least 30 years now. It has, in some sense, created a new subdiscipline. In the last 30 years, if you look at the most important research departments in physics all over the world, and look at the graduate students, the best graduate students, best theory graduate students from these universities, I do not know the statistics. I would say 50% of them are now in string theory. That very fact says that it is intellectually challenging. It is intellectually interesting. Otherwise, you could not entice thousands of these bright young people into it. And yet, it is not materialized. Not only it has not materialized into something which experimentally has been verified, it cannot even produce a statement for the experimentalists to say that you test this and you will be able to tell me whether my theory is correct. It has still, in some sense, an amorphous state. My experience with physics, this last 50 years of experience, tells me that it's not likely, let's say, in the next 50 years, that what has been done in string theory so far would enter into fundamental physics. I think that's very unlikely. But on the other hand, it has created a lot of excitement by the mathematicians. Now, one of the great mathematicians today is Atiyah of Great Britain. And he told me that not only has string theory produced things which are very important in mathematics, it has taught the mathematicians a lesson, namely that for many years, mathematicians emphasize rigor. But they now realize that these string theorists do not adhere to strict rigor. And yet they can produce things which were unthinkable to the mathematician to start with. But once pointed out, they found after some detour that in fact those are rigorously establishable. So that means that string theory is now a kind of a new subdiscipline, which so far the top mathematicians think is an important development, and they want to explore it further. So that is my opinion about string theory.
In the attractiveness of string theory to mathematicians, do you think there's a sign that it has passed a test of mathematical beauty, as opposed, which might be different than beauty for physicists or physics?
String theory goes beyond the 4 dimensions. And the geometry and mathematics of higher dimensions is extremely intricate and very beautiful. And apparently, I'm not in the field, but according to my mathematician friend, some of these explorations using physicists' intuition has produced non-rigorous mathematical results, which later turned out to be rigorously provable by mathematicians. Some of these have surprised them in their depth and, in some sense, strange beauty. Apparently, one idea, which according to Atiyah, in a conversation with me, was that there were 2 kinds of mathematical structures, which to the mathematicians are totally unrelated to each other. And the string physicists produced non-rigorous statement which said that the 2 are deeply related to each other. They are dual to each other, whatever that word dual means. And that shocked the mathematicians. And when they realized that, in fact, that statement is correct, via a rigorous route, they gained tremendous respect for what the string theorists are doing today.